So I'm Tom Peterka. I'm from Argonne. Thanks for inviting me. I'll try to run through DIY very briefly. So you've seen a couple of tools this afternoon and many features of them, right? It's been a long afternoon. Thanks for staying awake. But you know, all the things you've seen, nobody's asked the question, well, you know, what if I don't want a tool that does everything with all of these different features that have been explained, right? What if I just want to do my own thing, my own analysis, my own visualization, something very specific, very custom, right? Because there are a lot of computational scientists in the room, right? You may already know exactly what you do to your data, and you do the same thing every single time, right? And it may be something very specific to your science need, right? But you need to parallelize that yourself and scale that up to the full scale of your simulation because you want to run this analysis directly linked in with your simulation in situ. And you know, so you're not looking for something that does everything for you, but rather you would like some help in doing something very specific but at very large scale, right? In short, what if you want to do your own, do it yourself, parallel data analysis, right? So I asked myself this question a few years ago, this is an infrastructure that helps me and students that I work with and a couple of close collaborators, not terribly widely used, so not thousands of downloads or anything like that, fairly small project, in assisting us to parallelize our own analyses to very large scale and run them in situ directly in simulations in production mode, right? Some of the largest simulations running on HPC, very large machines. And yes, that is my wife and I on weekends, by the way. That's what our house looks like. And you kind of you've seen the motivation for doing this already a couple of times this afternoon, right? If you just do something in post-processing with a tool that requires you to first write all of your data out to storage, this big fat pipe, right, indicates very large amounts of data, and then a big fat pipe to some analysis cluster where you later look at it or analyze it, that could be very expensive, right? That data movement pretty much dwarfs everything else that you've done, right? So wouldn't it be much better at times to do, you know, analysis right here on the big iron, right, and result in kind of smaller pipes the rest of the way, right? And so the question is, how do you program very large, very wide analysis tasks running at tens of thousands of processes, not just a couple of hundred, right, that do something very specific that you want to do yourself, right? And so that's the motivation behind DIY. And analysis in my vocabulary could be pretty much any transformation that you do to raw data as it's being computed or being generated. It could be a visualization, parallel streamlines, for example. It could be some statistics that then you visualize. This, in particular, happens to be information entropy, a measure of the variance of a data set. It could be a complete conversion from a volumetric data set to something topological, a graph structure of the data, a segmentation of the data, and a graph representation of that structure. Or it could be something geometric, like taking a raw particle data set and meshing it into a polyhedral mesh of Voronoi tessellation, right? But whatever it is, I mean, we've done all these things. I'll show you performance numbers for these examples towards the end of this little mini talk. This is supposed to be success stories after all, so we'll highlight some of these successes. But whatever it is, you as a scientist, as a researcher, kind of know what it is that you want to do to your data. And every single time you run a simulation, you know that you want to do this. And you need something lightweight that scales up and that does that, you know, reliably and scalably at the same scale as your simulation does. And that's the one thing that you want to do over and over again. How do you write that parallel algorithm, right, to parallelize a Voronoi tessellation, right? Okay, something like that. Tools oftentimes have these features, but maybe they don't have the exact feature you need. Maybe they don't have the exact variation of that feature that you use every single time, right? Maybe the implementation of that feature of that operation isn't as scalable as you need, right? Maybe it only scales to a couple of hundred processes and not to, you know, a couple of 100,000, for example. Or it just plain doesn't exist at all, right? these are like the motivating cases why you might want to do your own analysis, right? And so through the years, I've been doing very large-scale parallel visualization or analysis operations, parallel volume rendering, image compositing at very large scales, particle tracing for flow visualization. And as I started to do these things over and over again, I started to realize that there's this common subset of communication and data movement tasks that I do over and over again. And I was literally copying and pasting code from one application and putting it into another until I got old, right? And that was the motivation for DIY, the DIY library. So you kind of have two ways that you could parallelize your own analysis. You have the old way on the left and the DIY way on the right, right? In the manual way on the left, I'm writing some algorithm, right? And what do? What would any of us do? You've been sitting here for over a week now. You know the drill. You start putting in MPI commands into your algorithm, and you start testing it, and you find deadlocks and race conditions and blah, 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 and you fix them, and then it starts to work, and you start to scale it up, and someplace there's a bottleneck, and you fix that, and you work through it, right? Like you really work through it, like for months or years, and you finally get something that works, right? And when you're all done, you go on to your next problem, and you start over again from a blank page, right? And so like I said, that's the way that I started. That's the way we all start, right? And after a while, you start to realize that this pattern here of these MPI calls, well, kind of repeats that. It's some kind of a global reduction or some kind of a neighborhood communication. It's some variant of a couple of core kernels that I'm starting to use over and over again, right? So wouldn't it be better eventually, right, to take that and include it into this middle layer here of a data movement library, right? And encapsulate large amounts of MPI code into individual, functions, right? And make them configurable in their arguments and so on, so that I could tune them for different machines and different problems and things like that, right? And eventually, be able to reuse that. So basically, putting this layer between the analysis algorithm that I want to parallelize and the MPI or whatever other parallel runtime I'm using, right? That's the idea behind DIY, okay? Stop me with questions at any time, of course. And so this is DIY. It's a small, lightweight parallel library. It's less than a megabyte, right? So no need to modularize. It's already small. It's a fairly small amount of code. So you've seen 20-year projects with 1.5 million lines of code. This is a couple-of-year project with 10, 15,000 lines of code. So fairly small. You could download this and you could actually read the source code, and it's not that bad. Autoconf build system. So for Mac and for Linux, right? Not for Windows. Sorry. Written in C++, but the API is C style. So you could run this in C and in C++. You could write wrappers for Fortran as well if you like to do that kind of thing. I don't, so we leave that for users to do. But we have done that before, and we know how to do that as well. The basic modules in DIY are parallel I/O, block decomposition, domain decomposition, a set of communication kernels for the commonly used patterns that I find myself and others using over and over again, and then some kind of standalone utilities that are useful in their own right. And we've seen this call stack in the previous slide too. So you have some analysis library, you have some runtime, and in between it you have this DIY library. You can also make calls directly to MPI. This doesn't intend to wrap all of MPI from you. It just does useful things that you would want to reuse over and over again. And then on top of this, you might still have simulations or some of the visualization tools that you've seen this afternoon. We, in the last 6 months or so, we've worked pretty closely with PairView and with Hank as well. But in particular, we've been working on integrating VTK and DIY so that some of the VTK filters now have DIY underneath as well. Not the production ones, but in a research sense. So there's closer and closer integration too of many of the technologies that you've seen this afternoon converging and coming together. And we're a pretty small community, so we know each other pretty well, and it's a very friendly and healthy collaboration as well. So things that DIY does, we can kind of name nine of them. Main main things that you would want to do, that you would need if you were parallelizing your own analysis. And the first is to recognize what are these data movement operations and separate them from the rest of your things that are specific to your analysis, right? That's this, that's kind of this line right here between things that are specific to what you're doing and things that are common to all of these problems, and that's what DIY is. So the first step is just to separate analysis operations from data operations. That's really the whole motivation for DIY, right? Then oftentimes you want to decompose your domain. These are data parallel problems, right? So there's domain decomposition, grouping data items into blocks. We call subdomains blocks. They don't have to be blocky. These can be regular structured grids. They can be unstructured grids. They could be graphs, whatever. Just whatever the unit of decomposition is, we call that a block in DIY. Assign blocks to processes is sort of a, seems obvious, but it's actually, there's a little more going on there. One of the main tenets of DIY is that the block is the fundamental unit. Blocks communicate with each other, not processes communicating with each other. And the mapping of blocks to processes is determined by DIY at runtime. So you could run the same program with, of these 8 blocks on one process where they're all colored the same, or on 4 processes where 2 of them are the same process, or on 8 processes where each one is colored differently by process, right? To DIY, that's all the same program. You write that program once, and you choose to run it on different size machines. So it's blocks communicating with each other, not processes. And that's what DIY does. It basically divides a problem into blocks and communicates information between them. And so this assign of blocks to processes is actually a legitimately important step that should not be overlooked. Okay. Then the next level of grouping is to group blocks into neighborhoods. So when we do neighborhood communication, here's an example of a structured grid. If this is a block, its neighborhood could be the physically adjacent blocks around it. It's up to you how you assign neighborhoods. DIY will do kind of the regular structured grid itself for you. So, but you could, a neighborhood could in fact be anything that you want. But when we do, if this block were to communicate with its neighbors, it would be the other blocks that are considered within its neighborhood. And that's a way to kind of localize and compartmentalize the communication. We can do global communication as well as neighborhood communication. But when we do neighborhood communication, this idea of having neighborhoods is key. And DIY helps you create neighborhoods and manage them. And then we can have entire multiple instances of these things. We call them domains. That is, different decompositions into blocks and different groupings of blocks into neighborhoods, right? We can have multiple instances of that at the same time in DIY, and we can communicate between those instances. So sometimes one task you might want to do demands a particular decomposition, maybe nice blocks. A different task maybe runs better with a different decomposition, like slabs or pencils. You can maintain multiple instances of these at the same time in DIY. Number 6, DIY handles time natively. This is sort of a diagram of a spatial neighborhood and a temporal neighborhood. Internally, these are all 4D entities in DIY. But we can kind of handle both time and space all unified, or we can separate them out, whichever is more convenient. And we do all of that natively. Right? That was all built into DIY right from the start. All science problems that we deal with are time varying, so this is absolutely essential to handle time in our analyses. The communication between blocks, we have 3 different modes, 2 global reductions and 1 neighborhood communication. I don't have time today to go into the details, but there are entire papers written on these algorithms. There's a complete body of research into handling this communication efficiently and scaling it up to very large scale. There are benchmarking papers and so forth that prove that these communication algorithms are actually very good. You'll see, all I can say today is kind of we'll look at the results that I show you, and hopefully that'll convince you, or at least whet your appetite, that these are good algorithms. We do some parallel I/O, both reading in raw data and writing out analysis results. And we play well with other libraries and tools. So you've seen throughout the week and a half lots of different tools, even today, several of them. And you know, you as a practitioner of your work obviously have kind of your tool chain that you like to use. And it's important for DIY not to expect to replace all of those, right? But rather to integrate with them. And there are specific ways that I won't cover, but that we both integrate inputting external data models from other tools, as well as exporting external file formats in using ParallelNet CDF or HDF, for example, or other formats. So DIY was always designed never to be an all or nothing proposition. You could use just the domain decomposition from it, or just the domain decomposition in the communication. You don't have to use all of it. It's an API. It's a library. You pick and choose from it the things that are useful to you. So as I said, it's a library. It's an API. You write a C or a C++ program, and you make DIY calls wherever you want. But normally these programs look something like this flow chart on the right, where you do a DIY initialize. DIY can decompose the domain for you, or you can provide, for example, if you're a simulation and you want to do in situ analysis, you can provide a specific domain decomposition already and simply tell that to DIY. This is the decomposition I'd like you to use. You can use DIY to read raw data in from storage, or you can read it in yourself, or it may already exist in memory if you are in computation and that data is already there. You write your own local serial analysis. You do some local computations. This is why it's called DIY, right? You provide that. Now, it's important to realize that you don't have to necessarily write this from scratch. You might find an existing serial computational geometry library, for example, which is what we did in the Voronoi tessellation work, and simply use that. That's perfectly fine, too. There's just another nice feature of being able to integrate with other existing tools and libraries, right? So whatever it is, you provide your own local algorithm. You use DIY to do one of these three communication algorithms, and you can repeat that as often as you like, and you can use different communications at different times. You can make this program as complicated as you want, because it's just a program that you're writing, after all. And eventually, when you're done, you will probably want to write some analysis results out to storage and call DIY finalize. So the DIY repository has a README for installation, has a user's manual, basically a reference manual of the complete API. And best of all, it has lots of examples that follow kind of this pattern, but they're very small. Complete toys, 4 processes, 8 processes, whatever, just absolute fake data. I mean, just demonstrating the concepts, but they're so nice and compact that they're readable and they're easy to digest. So in terms of actual success stories, which is what I'm supposed to be talking about, and I've got no time left, but that's okay. We'll cover 4 or 5 of these very quickly. The first one is flow visualization, parallel particle tracing of streamlines and path lines for steady state and time varying flows. There's an image on the right, and generating the actual streamline tracing out to 32K processes, right? On all these graphs, the horizontal will be the number of processes. The vertical will be time, so lower is better. We expect these to always go down and to the right, right? And you'll always see an ideal scaling curve. So these will always be strong scaling curves, right? Problem size will be the same. We'll add more and more processes, and we'll compare, pre-DIY to the DIY version is about 2 times faster. This was our old version, and pretty reasonable for this problem size with respect to the ideal scaling. This, in particular, was a 250,000 particles traced in a 2K cubed thermal hydraulics data set, going out to 32K processes. In this next example, we took a much smaller data set, 126 by 126 by 512, ran this out to only 1,000 processes, but had very good strong scaling for an information entropy application. This is converting a raw volumetric data set to its Shannon's entropy, basically computing the information entropy at each voxel within the data set, and then rendering it, then coloring it, right? But the computation of the entropy is what is being plotted in the performance graphs right? Typically, in most of these examples, or in all of them, the computation of the transformation of the data, which is what I would call the analysis, is what's being done on the big machine at scale in situ. The rendering is typically done offline in post-processing. That's just so that we have some image to show and some representation of the problem. But it's always the thing on the left, the actual computation of that data transformation is the thing that we're doing at large scale in situ on the big machine. And that's sort of like the workflow that I like to use. The third is topological construct. The Morse-Smale Complex is a segmentation of a data set of a scalar field according to its gradient behavior. So into regions where the gradient flows the same direction. And basically, these are separated by critical points, minima, maxima, and saddle points, and the lines that separate those, that connect those points separate the regions. And here to compute this Morse-Smale complex, Hank showed this example earlier. This is the Rayleigh-Taylor instability on an 1152 cubed data set out to, again, 32K processes, was strong scaling efficiency of 35%. So 35%, you know, if this followed this line exactly, it would be 100% strong scaling. This was 35% strong scaling. It's important to note that all of these scalability curves include I/O as well, not just the computation. So this is end-to-end. So, you know, this is what you see is what you get. There was a question. Well, so why the deviation from this line, basically? Well, I mean, I would say, you know, the reasons are that it includes I/O, right? It includes everything. I mean, if you're a computational person, you would say, well, my strong scaling is 80% or 85% or something like that. But that normally doesn't. That normally includes just your innermost loop of your computation, not everything, right? So that's one thing, is that this includes everything. I/O is usually the biggest part of that, which is another testament to DIY's I/O, parallel I/O routines, as well as the rest of it. The other thing is that you know, data analysis is different than computation. I mean, normally if you're doing, you know, if you're computing a differential equation, you don't think a whole lot about data movement and communication. You're worried about optimizing your innermost loops, right? Your linear algebra routines like that. And the occasional communication you have to do is just noise, right? Data analysis is like exactly the opposite, right? There usually isn't a whole lot of computational intensity to hide the data movement. Right? These are typically closed form things that are not iterative. They're fairly simple to compute. Right? There just aren't a lot of flops to mask the data movement. Right? So these are like the hardest of the scalability problems to try to scale. And we think that the numbers that we've come up with aren't too bad. There's always room for improvement, obviously. But those are some of the reasons why. Oh, yeah. Yeah, absolutely. I mean, typically all of these problems are trying to resolve something non-local or global from a distributed memory space, right? Which we again, consider to be kind of the hardest scaling problems. And you're having to communicate all the time because you just don't have the compute intensity to hide that, right? The communication here is everything, and the I/O. And that's really what DIY does for you. And the last one here is computing a Voronoi tessellation from a particle data set. So this is an n-body simulation of cosmology. You've probably seen the hack simulation earlier in the week or last week. That's this code with Voronoi tessellation embedded directly into the code and running, you know, production inside of it, right? And here on a couple of different test problems. So Voronoi tessellation is a mesh, basically where the size of the cells are proportional to the distance between the particles. It's like a complete meshing of a particle data set that self-adapts to the spacing between the particles, right? And here on 4 different data sets, ranging from 128 cubed up to 1024 cubed, smaller to bigger. We ran out to 16,000 processes. And for like the 128 cube, for example, this one here, we had 41% strong scaling efficiency. This, in fact, was about comparable with, at the time when we ran this, with the code's strong scaling as well. So we were like right there, scaling about as well as the simulation code itself, fitting into its memory space so that we didn't run out of memory, right? We added more work to the code because it ran our analysis in addition to running itself, right? All in the same space. We scaled along with the code and fit, within its memory constraints as well. And these are the things that you want to do when you're trying to, embed an analysis directly into a simulation, right? You have to scale with the simulation, and you have to fit within its memory constraints, right? And within its timing as well, right? So you have to take up a small fraction of the time to do this. You don't want to use all of their cycles to do your analysis, right? You have to scale with the size of the problem, with the size of the machine, and with the size of the memory. And so most of these things have been documented in papers that you can reference. There are kind of two basic papers on DIY itself, the original paper and then a benchmarking paper. And then all of the applications that I've shown and a couple others that I haven't shown are in this second set of papers that are more specific to the analysis task, but each of those tasks is parallelized on top of DIY and published. So I invite you to refer to those later. And with that, I'm happy to take any questions, and otherwise I think I'm handing off to Joe. Yes. While we're changing, are there any other questions? No? Great. All right, thanks again.